Welcome to the channel.
Imagine you're a detective, but your crime scene, it's 13.8 billion years old, and your suspects are scattered across the entire expanding universe. Welcome to this explainer. We're going to dive straight into the ultimate forensic investigation, unraveling the absolute mystery of galaxy formation. You know, galaxies are basically the building blocks of the cosmos. They're tracers of cosmic expansion, marking those tiny primordial density fluctuations that literally gave rise to every structure out there. But how exactly did these massive, incredibly complex cosmic cities actually come to be? Well, we're going to examine the evidence, break down the physical laws, and piece together exactly how our universe grew from this smooth expanse into a giant web of structured galaxies. Let's get into it.
All right, to kick off our investigation, we've got to confront a massive roadblock right out of the gate. 85%. Think about that. If you look up at the night sky, literally everything you see, every twinkling star, every glowing nebula, every single swirling galactic arm, that is just a tiny, tiny fraction of what's actually out there. A staggering 85% of a galaxy's mass is completely invisible to us. It doesn't emit, it doesn't absorb, and it doesn't reflect light. Nothing. This is our primary cosmic mystery, right here, and it completely dictates the terms of everything we're about to explore.
Part 1. Anatomy of a galaxy. Let's build our suspect profile.
So, looking at our galactic mass budget, the vast majority, that wild 85% we just talked about, is held by dark matter. This invisible stuff basically forms an enormous spheroidal halo, completely surrounding a galaxy. It's like the hidden architectural scaffolding of the universe, and its gravitational pull absolutely dominates the whole system. The remaining 15%? Well, that's what we call ordinary or baryonic matter. That tiny little sliver represents all the hydrogen, the helium, the stars, the planets, and, well, us. While dark matter pulls the gravitational strings, this small visible fraction is literally the only part of the galaxy that emits electromagnetic radiation for us to actually detect.
Okay, so let's break down that visible 15%, the suspects we can actually see. We've got gas, mostly hydrogen and helium, which acts as the raw fuel for forming new stars. We've got dust, which traces these incredibly rich star-forming environments. And, of course, we have the stars themselves, which give off the bulk of the visible light. But here's a real wait-what kind of fact for you. Nestled right at the center of these galaxies, we find supermassive black holes. We're talking millions to billions of times the mass of our own sun. As gas falls into them, they can power active galactic nuclei, spitting out just enormous amounts of energy. And incredibly, the energetic output from these central black holes can actually regulate star formation across the entire scale of the host galaxy. It's totally wild.
Moving on to Part 2, the Cosmic Detective Toolkit, Investigating Light.
Since we can't exactly visit these places, our primary tool is light itself. Specifically, we use something called spectral windows. Now, in astrophysics, when we talk about color, we're essentially defining how much light, or flux, passes through very specific filters across the electromagnetic spectrum. By looking at a galaxy through different spectral windows, it's like we're swapping out forensic lenses. It allows us to literally peel back the different layers of physical processes that are happening all at the exact same time inside a single galaxy.
Let's actually see this in action using the nearby spiral galaxy M81. On the left, we flip our lens to the X-ray window. And suddenly, we aren't seeing stars anymore. We're seeing diffuse, extremely hot gas and these intense point sources like X-ray binaries. You see that really bright central source? That is the X-ray signature betraying the presence of that supermassive black hole we just talked about. Now, shift over to the right, to the ultraviolet window. The black hole completely fades from view, and instead we uncover these brilliant, glowing sites of massive young stars. UV light perfectly highlights the exact locations where star formation is going on right this very second.
Now let's contrast that with the exact same galaxy viewed through 3 totally different windows. The optical view, over on the left, shows us the bulk of the standard stellar population. You know, what you might see in a normal visible light photograph. In the middle, the infrared window bypasses all that starlight to reveal the glowing dust that wraps around those star-forming regions. And finally, the radio window on the right gives us a completely different map, highlighting resonant emission from neutral atomic hydrogen gas. Every single window gives us a brand new piece of the cosmic puzzle.
But here's where we really have to pivot. Taking pictures of galaxies across the whole spectrum is incredibly useful, sure, but it doesn't give us the hard numbers we need. Think about it. If 85% of a galaxy is completely invisible dark matter, how do we weigh a galaxy we can't even touch?
We can't just rely on pictures. We need to analyze the physical properties literally encoded inside the light itself.
And that brings us to spectroscopy. Basically, we take the light from a galaxy and we smear it out to look at its spectrum. Those little dips you see, those are absorption lines, and they originate straight from the atmospheres of the galaxy's stars. Spectroscopy acts just like a cosmic fingerprint. Because the stars in a galaxy are constantly moving, the Doppler shift alters the position and shape of these lines. So, in a massive galaxy loaded with a ton of invisible dark matter, the massive gravitational pull causes the stars to move with a higher velocity dispersion. Basically, they're buzzing around much, much faster. That high velocity causes these spectral lines to become significantly broader. By measuring exactly how wide these lines are, we can actually calculate the mass of the invisible dark matter that's pulling on those stars. How cool is that?
Part 3. Decoding galaxy shapes. Morphology clues. All right, check out the famous Hubble tuning fork. It so neatly divides our galactic subjects. We see a very clear split here. On the handle of the fork, we've got the elliptical galaxies, which are really smooth and spheroidal. And then, branching off to the right, we have the spiral galaxies, which split into your standard spirals and barred spirals. Now, these aren't just arbitrary shapes we made up. This diagram actually represents two very distinct evolutionary paths, completely dictated by the laws of physics. Let's compare these two paths for a second. Early-type galaxies, the ellipticals, are spheroidal. Their internal motion isn't some neat, organized rotation. It's honestly more like a chaotic swarm of bees, supported by pressure rather than a unified spin. They're absolutely full of old, metal-rich stars, which indicates they formed their stars very early on and very efficiently. So why are they shaped like this? Well, the evidence heavily points to major merging events, massive, violent cosmic collisions that basically scrambled the orderly orbits of any disks that might have been there. On the flip side, we have late-type galaxies, the spirals. These are flat, rotating disks. They actually form from gas collapsing under gravity while holding on to its angular momentum. It's exactly like a spinning figure skater pulling their arms in to spin faster. And unlike ellipticals, spirals feature a real mix of older stars and ongoing young star formation.
But we definitely can't forget the irregular galaxies. This is basically the disorganized everything else category. They don't have a smooth, elliptical shape, and they definitely don't have the graceful, sweeping arms of a spiral. But what's absolutely crucial to our investigation here is that when we look deep, deep into the cosmos, and therefore looking far back in time, these messy, irregular galaxies become much, much more common. This is a massive clue for us. It tells us that galaxies looked completely different in the distant past, which leads us perfectly into our final mystery.
Part 4. The Formation Mystery. Building the Cosmos. To figure this out, we have to go all the way back to the universal starting point. Right after the Big Bang, the universe was rapidly expanding, stretching all its matter out very, very thinly. But fighting directly against this huge expansion was our old friend, gravity. Within the first few 100,000 years, gravity actually began pulling this generally diffuse matter into denser and denser clumps. Over the next few billion years, these clumps collapsed under their own weight to form the very first proto-galaxies. But the huge question that really divided scientists was, what did those original proto-galaxies actually look like?
Historically, there was a massive theory face-off over this. Back in 1962, the classic top-down theory proposed that giant, already galaxy-sized gas clouds existed right near the beginning, and they collapsed all at once to form the giant, mature galaxies we see around us today. But you know, science marches on. That idea has been largely superseded by the modern bottom-up theory, which is also known as hierarchical clustering. This modern model suggests that small proto-galaxies formed first and then slowly grew massive over billions of years through a pretty violent history of repeated mergers.
So, the absolutely crucial point here is that the bottom-up model perfectly integrates our hidden suspects, dark matter. The gravitational pull of dark matter acts as the ultimate framework. Small clumps of dark and normal matter merged into larger clumps, building the vast structures we see today literally like cosmic Lego bricks. Instead of starting out huge, the universe started small and just built its way up through a constant chaotic process of galactic mergers.
And the absolute smoking gun for this theory comes directly from observational evidence. When we use incredible instruments like the James Webb Space Telescope to look billions of years into the past, we don't see massive, beautifully structured spirals. No way. As NASA points out, the most distant galaxies look distinctly smaller and way less well-structured. We are literally catching these early messy mergers in the act. The universe is a dynamic, sometimes violent place, and galaxies evolve incredibly dramatically over time. So we've pieced together how invisible, dark matter, collapsing gas, and billions of years of violent mergers construct the majestic galaxies we observe today. But, this process isn't just ancient history. It's happening right now. In fact, our own Milky Way is currently on a collision course with the neighboring Andromeda galaxy. So as we close out this explainer, I want to leave you with this final spectacular mystery to ponder. When our own galactic neighborhood experiences its next major cosmic merger billions of years from now, what magnificent, completely unrecognizable shape will our new galaxy take?